Hi everybody! So now that we know how to find antiderivatives and we've practiced that a little bit, let's talk about how we can use them to find exact area. So here's what we know so far. We know that we can find exact areas using geometry. But this only works for geometric graphs, graphs that have nice semicircles or triangles or rectangles. We also know that we can approximate areas using LRAM, RRAM, MRAM, or the trapezoidal rule. But the disadvantage of this is it doesn't give us exact areas, it just gives us estimates. So our big question of the day is how can we find exact areas when we don't have a geometric graph? Well, here's the thing. If f is continuous between a and b, and big F is the antiderivative of little f, then the integral or the area is equal to the antiderivative with little b plugged in first and little a plugged in second. And then we just subtract those two numbers. Now, why is this important? Well, it means that we can use the antiderivative to figure out the area under a curve that is not nice and doesn't have a geometric shape. So let's look at some examples. By the way, this is called the fundamental theorem of calculus, which basically says derivatives and integrals are opposites of each other, so we can use antiderivatives to help us figure out integrals. It's really important. They don't call it fundamental just because it's like a sort of important thing. Like, it's the most important thing in calculus. So, use antiderivatives to evaluate the following integrals. Step 1 is to figure out the antiderivative. So here's how we write this, and it's going to be really important that you show notation correctly, that you show your work the right way, etc. First, we find the antiderivative. So we're going to do one term at a time. The antiderivative of 2x would be x squared, and the antiderivative of 2 would just be 2x, and then we have a plus c. That's the antiderivative. Then the notation looks like this. We draw a big vertical line, and we put the 0 at the bottom and the 3 at the top, the same bounds you had here. And this line means evaluated between. Next, we plug in the 3 for all of the x's. So, first I'm going to plug in the 3. I'm going to have 3 squared minus 2 times 3 plus c minus, and now I'm going to plug in the 0. So 0 squared minus 2 times 0 plus c. And now we're going to simplify. So 3 squared is 9, minus 2 times 3 is 6, gives us 3 plus c, minus 0 plus minus 0 plus c, so minus c. And then c minus c cancels, so our answer is just 3. What this means is, if you graph 2x minus 2 and you evaluate it between 0 and 3, your area should be 3. So just this once, let's see if we can confirm this graphically. So just this one time. The graph of 2x minus 2 between 0 and 3 looks like this. starts at -2, it goes up 2 over 1. So it's a line that looks like this. Asking me to evaluate the integral from 0 to 3 means figure out these areas. Now this bottom area is going to be negative because it's below. So we're going to have -1/2 because it's a triangle. Base is 1, height is 2. Plus, now the next triangle is above. So 1/2, base is 2, height is 4. This is going to end up simplifying to -1 plus 4, which is 3. So figuring out the antiderivative, plugging in the 3 and then subtracting and plugging in the 0 gave me the same area that I could get geometrically. And the nice thing is that it's also going to work for graphs that we cannot figure out geometrically. So for the next problem, step 1 is going to be to find the antiderivative. The antiderivative of 2e to the x is just 2e to the x plus c. Then we draw a line and we write evaluated between -2 and 0. Now we're going to plug in the top number first, and we get 2e to the 0 plus c minus, and we're going to plug in the bottom number second. So we're going to have 2e to the -2 plus c. And now we're going to simplify. Now 2 times e to the 0, well, e to the 0 is just 1. So it's going to be 2 plus c minus 2e to the -2 doesn't simplify, plus c. I'm going to go ahead and distribute that negative. So I'm going to have 2 plus c minus 2e to the -2 minus c. I just distributed the negative, which means the c's cancel, and we end up with 2. Oop, you can't really see what I was writing there. I apologize for that, guys. Go ahead and pause the video if you need to and copy that down. 2 minus 2e to the -2 is our final answer. Now this one would be impossible for us to figure out algebraically, which is why this method is so useful, is it allows us to do problems that we couldn't do geometrically and get exact answers. On the next page, let's try a few more. So for number 3, if I said figure out the area underneath a secant squared graph between pi over 6 and pi over 4, step 1 would be to figure out the antiderivative. Well, the antiderivative of secant squared is just tangent plus c, evaluated between pi over 6 and pi over 4. Now I would plug in the pi over 4 first. So I would have tangent of pi over 4 plus c minus tangent of pi over 6 plus c. Tangent of pi over 4, if you think about the unit circle, is just 1 plus c minus tangent of pi over 6, if you think about the unit circle, is 1 over root 3 plus c. If I distribute that negative, I have 1 plus c minus 1 over root 3 minus c. So the c's canceled, and I get 1 minus 1 over root 3 as my answer. For number 4, if I evaluate this integral, I'm going to need the antiderivative. The antiderivative of sine is negative cosine. So we would have -2 cosine of x plus c evaluated between pi over 2 and 5 pi over 6. I'm going to plug in the 5 pi over 6 first. So -2 cosine of 5 pi over 6 plus c is the first part, minus -2 cosine of pi over 2 plus c is the second part. Now 5 pi over 6, the cosine value of 5 pi over 6 is square root of 3 over 2. is negative square root of 3 over 2 plus c minus, now cosine of pi over 2 is 0, so it would be 0 plus c, which means if I distribute that minus, I get the 2's cancel, I just get the square root of 3 plus c minus c. The c's cancel, and I get the square root of 3. For number 5, if I want to know the integral between 1 and root 3, the first thing I need to know is the antiderivative, and the antiderivative of 1 over 1 plus x squared would be inverse tangent of x plus c evaluated between 1 and the square root of 3. So I would plug in the square root of 3 first, plus c minus inverse tangent of 1, plugged in second, plus c. The inverse tangent of the square root of 3, well, tangent is going to be square root of 3 at pi over 3. So I would have pi over 3 plus c minus the inverse tangent of 1 is going to be pi over 4 plus c. If I distribute that negative, I have pi over 3 plus c minus pi over 4 minus c, so the c's cancel, which means I just have pi over 3 minus pi over 4. If you wanted to make a common denominator, you would get pi over 12. For number 6, if I want to figure out the antiderivative, I need to remember that when there's an x in the bottom, the antiderivative is the natural log of the absolute value of x plus c, evaluated between 1 and 4. So I would plug in the 4, minus, and then I would plug in the 1. The natural log of 4 is not something that I know, and I don't need the absolute value anymore because it's already positive. The natural log of 1, however, is 0. So I would just have minus c, the c's would cancel, and I would have the natural log of 4 as my final answer. I'm going to go ahead and stop there. Hopefully you've kind of gotten an idea of how this system works. Antiderivative, plug in the top number, subtract, plug in the bottom number. And we will talk about this some more tomorrow. We'll practice it, and we'll do some practice problems together. So thank you so much for watching, and have a great night, and I will see you tomorrow.